Hello and welcome to the third video from the Introduction to Our Workshop series run by QIMR Berghofer Statistics Unit. The Introduction to Our Workshop series is a series of 5 hands-on workshops. This third video relates to the last part of the first workshop. Statistics Unit, as I mentioned before, provides lots of services to QIMR Berghofer, Metro North, and MARTA Research, and there are our contacts. Hopefully, by the third video, you've at least downloaded R&R Studio and have the booklet to work along with. That's the booklet that relates to all the material from the workshops. So if you're not familiar with R, it's probably best to at least touch on those first videos first. Hopefully you've also run some of that code on the left of the screen there for installing the packages. The previous video went over how to install packages in a bit more depth because we will be using perhaps some of those functions today. We'll also be using that first data set, the pulse data text, more specifically the week 1, 9, and 10 and week 3, 16 pulse data text. CSV file there, we will be using that today. So it'd be good for you to have got that data set if you want to work along with a video, and also to know exactly where that data set is saved on your computer. So this video relates to sections 9 and 10 from the booklet, and these are the last 2 sections from the first workshop. So this video will be looking at reading in or importing data into an R session, and also just some basics on inspecting and looking at data once you have it in there and understanding what type of data you have. So reading in data, also referred to as importing data. It's generally often just referred to as reading because all the functions, or most of the functions, have read as part of the name, and many of those functions have a very similar form. So most of the functions for importing data, the function name starts with a read and dot, and then some other name to signify what type of file is being read in. So that's generally the most common. There are some variations on that, but that's generally the most common way. And there are many different file types that can be imported into R, depending on what packages you have available. So in basic data format is the simple text file or a .txt extension file. So that can be read in with the read table function. So that's read.table or lowercase. Your first argument to that function is the file name you want to read in with the .txt extension included, all of that enclosed by quotation marks. So that first argument that is the file name you want to read in is a character value. And we talked a bit about in previous videos when we look at functions of the arguments of functions and what type of value those arguments take. The name of the file needs to be a character type. So that's why it's in quotation marks, and it also needs to include that extension at the end of it. Some of the arguments I have up on the screen now in the functions may not be necessary. So often some of the arguments like header and sep will have default values. And so you don't necessarily need a given input to them, but often it's good just to include it to make sure you're very clear when you're writing a code to know what's happening. The header argument basically says whether the first row of your data contains variable names when you call in the data set. So if you have a data set where the first row is variable names, you can say header is true, and that row will be read as the names of your variables in your data set. If you don't have that line in your data and your data is just the straight values, there's no names to what each column is, you can say header is false and it won't try and read the first row as variable names. That sep argument stands for separator. So in the .txt file, you might use a comma to separate rows of use a comma to separate columns of data. You might use a hyphen, you might use some other symbol, or you might use tab, so where every column is separated by a tab or a certain spacing, and so that \t enclosed in quotation marks means tab. So it'll be read as tab when the function reads in the file. Next we have the read.csv file. So that's for reading in CSV files or comma separated variable files. So the type of files that are often read into Excel, and they're just like very simple versions of Excel files. Only have one sheet, don't really support a lot of functionality such as equations. It's just a way to store data. And there, so you don't necessarily need the step argument there. Header equals true is just there to remind you so that you can definitely say that the first row of that data is variable names. But of course, you don't need that with the defaults. The next thing we look at there on the screen is the .xlsx file, which is your modern Excel file. So earlier versions of Excel would have had a .xls extension, whereas the current Excel has a .xlsx extension. So Excel files are the ones where you can have sheets of data and generally have it from the Excel document. There's lots of different ways to call in Excel files. One common one is using the read.xlsx function from the package xlsx. So on the screen there's the first line of code, which would be library xlsx. So if you've got the xlsx package, library it in, and use the read.xlsx function. You then have the name of the file with the .xlsx extension included in the name. Header is true there for the first row of data to be the variable names. And then sheet index is one, meaning the first sheet in the file is the one you're reading in. Because Excel files can have multiple sheets, you need to say which sheet is being read in. Even if there's only one sheet in the file, you still need to say which sheet index, or alternatively, a different version of the argument can be sheet name. I'll talk more about this later. We can say which sheet name to be read in. That way it's just forcing you not to rely on just calling the first sheet in by accident. The thing with the xlsx function, the xlsx package and read xlsx function, and many functions and packages like it, is that it relies on Java as a background software when dealing with Excel to import data. So when you use the read.xls function to call in an Excel file, Java works in the background to get the data out of the Excel file for you. And that can be okay if you have got Java on your computer and R and Java and Excel and everything is playing nice together. That can work fine. But for reasons generally beyond my understanding, sometimes that just doesn't work. And so using read.xlsx can have issues there. An alternative to this is the read_xl with Excel spelled out function from the read XL with just an X and an L package. That's the one below the xlsx one there. Read_xl function doesn't use Java as the background, doesn't use Java in the background, sorry. So it still has the file name as a string, as a character value. The arguments for the variable names and the sheet number are a little bit different, but essentially the same concept. And so using that function means you won't have to rely on Java. Why did I mention the read.xlsx function in the first place then? The xlsx package has a lot of other functions for writing .xlsx files. So there's a great deal of functionality there, whereas the read_xl package really only deals with reading in and importing data. So the xlsx package has a lot more that it can offer you if you can get it to work with Java. If not, there are lots of workarounds. There are lots of packages that have been developed for working with Excel data because so many people use it. You'll notice that read.table and read.csv didn't have a library in front of them, so they're base functions. well, they come with the initial download of R, whereas most of the functions that deal with XLSX files do come from an alternate package. And there are a number of packages that deal with that. I've just got the two of the most common ones there. So .txt, .csv, and .xlsx are probably your potentially most common file formats. There are many other type of file formats you can get. You might have data that is already saved as an SPSS data file, or a Stata data file, or a SAS data file. There are other packages that can deal with that. So if you want to look into that, there are the packages foreign and the package haven. Both of those have functions within them that can deal with those statistical software data sets. And then you can always just check the internet as well. There's lots of different ways to call in data. Like I suggested, each read function is fairly similar in terms of arguments, but it's really important to check the documentation around the function that you're using, to make sure you know what arguments are being called and what the input to each argument needs to be, and what it's going to give you in the end. So that's always important to check, especially if you're not really familiar with the function, and we'll look at the documentation in just a second. The output from all of these read functions are a data set that gets called into R. So the output from that function is a data set, generally a data frame. But if you want to save that data set into your session and use it, so if you want to call it in so that you're able to manipulate it and do analysis on it, you do need to assign it to an object. R isn't one of those softwares that only deal with one data set at a time. So it's not like you can just call in one data set and that's the one data set we're using. It's not like others where you call in a data set and that becomes data set 1. You can call in other ones and it becomes data set 2 and data set 3. R is a lot more flexible, but you also have to be a lot more specific with it. So when you call in a data set, you have to assign it to an object, and then you can do all your work on that object. So for example, here, that code above the picture would call in the data set and save it as the object pulse_data, and it would appear in our environment as an object called pulse data of 110 observations of 12 variables. But if we quickly go into R to look to see how that would work. Okay, here I am in my R session. So yeah, obviously before you do this, you'd want to set your directory to where the data set is saved so that R knows where to look for it. We covered this in the last video on how to get your working directory and how to set your working directory. So using the setWD function with the input of the character, the input being the folder, the pathway to the folder you want to be working in, and that's the folder where you've saved this data set already. I've already done that previously, but you'd need to do that beforehand. So if you haven't done that yet and you want to work along with the video, pause and find where you save the data set, get that pathway, and set that as your working directory. Remember, the working directory doesn't include the file name, it's just the pathway up to the folder where the file name is stored. Okay, next we're going to use the Read Csv function. Now I'm not including any other arguments because by default header is true and all those other things like that. But of course I could always look up the Read Csv function. So I'm going to go over here to my search bar. There's many different ways I could look up the information, so I could always use read.table. I could use help bracket read.table in quotations, or up here I can go read.table, give me some suggestions. actually, sorry, I'm looking up read.csv. Apologies for that. But both read.table, read.csv, and read.delim are all part of the same documentation. So I can see here for read.csv, file is the first argument, so that will be the character value of the file name. Header is by default true. Sep is by default a comma because it's a comma separated variable. There are other arguments there that generally won't affect how we call in our data, at least not for our example here, but I do encourage you to look them up some other time. You can go down here to the arguments and it gives you a description of all the arguments there. Another useful thing is, depending on how updated your Studio is, if you hover your mouse over the function, it'll give you a little prompt to say what some of the common arguments are that you might need. So it might just help you, remind you as you start writing out the function what the names of the arguments are, because that can be sometimes what I find the trickiest thing is. I know what I need to give the function, but I just sometimes can't remember what the arguments are called or what order they're meant to be in. So sometimes it's best to look that up fairly regularly. Anyway, so I've got my read CSV as the function. Inside the brackets is the name of the file with the .csv extension all in quotations. I can see it's all good because because it's character value, it's colored differently, contained within the quotations. And I've got my assignment there, meaning that the output of the read CSV function is going to be assigned to an object that I'm going to call pulse_data. So with my cursor on that line, I'm going to hit Control Enter. And I can see here now in my environment that I have a data object that contains 110 observations of 12 variables. Awesome, so that's essentially how you read in a data set. Use the appropriate read function, assign the output to a data set. If I didn't assign it to an object, I'll go down here to the console and go up to the previous line. If I had just done read CSV function without assigning the output would just be printed to the screen. So I'd see the data set that's there, but I can't do anything with it. It's a big data set, so it's not even showing me all the data that's there. I can see the data set, but I can't do anything with it. So I do have to assign it to an object so that I can use the data. Okay. So encourage you to do that if you're working along with the video or working along with the booklet. Once you have imported that data set, preferably do call it pulse_data like I have. That way the code you write should match the code that's in the book and the code that I'm using. And now we'll look at a few ways to explore and understand and get to know the data you've called in. This won't necessarily be in depth, it'll just be looking at a couple of different ways and a couple of different functions you can use to call in your data. So set your working directory, use the read CSV function on the function file, and call it in. If you get errors, double check that your working directory is set correctly. Double check there's no typos in the file name you're using. If you have any other errors, feel free to hit Google up. Google is your best friend. And then we will keep going. Okay, so the first part of knowing your data is we're going to look at like really quick ways to see your data. One thing obviously we can do is if I take my mouse over here to the environment tab and I click on pulse data, the data set appears here next to my scripts. So I can see my data set, I can see the variable names, and I can scroll through it. So I can scroll up to subject to 110. Now this can be fairly useful if you've got small to medium sized data sets. If you've got very large data sets, this isn't as useful. So if you've got hundreds and hundreds of variables, hundreds and hundreds of rows, looking at it this way may not necessarily be as useful. But so it really depends on how you're using it. One thing I will show you here when we're viewing the data is we can hover over each variable name, and depending on your version of RStudio, but if you've downloaded it recently, this should be the case. Hovering over the variable names will tell you some information about them. So it tells you what column number you're looking at, which can be very useful if you're trying to extract information out of it. It also tells you what type it is and what range, if it's new stuff like numeric, what range it has. If it's a factor, it tells you how many levels and things like that. We can also use these arrows next to the name to sort the data. So by clicking height there, I've sorted height ascending. You can go height descending as well. I can do the same for female or male. And I can also hit filter. This is much like you can do with Excel. So here I could filter out, so I could just have the high exercise cases in the data set and cancel that as well. And then also just revert back to normal. That doesn't change the data in any way, it just changes how you're viewing it. Because if I close that data set and then open it back up again, the filter's gone, nothing's changed about it. But that can just be a useful way to inspect your data and work with it that way. Or the filtering and sorting can also be a good way to clean your data by looking for strange values. Going back to my script here. So that works really well if you've got a reasonable sized data set. If you don't have a reasonable sized data set, if your data set is very large and looking at it visually that way may not be easy, there are some functions that you can use to help you. So there's the head function. So head in lowercase, and you just put the data object there. So the data set we have, if we're referring back to video 1, is a data frame. That's what pulse data is, and that's what the output of the read.csv function was. So I'm just going to put my cursor on that line 34, Control Enter, and head outputs to the screen the first 6 lines, first 6 rows of the data set. So I can see the first 6 cases. Notice here also on the left, there's these numbers that seem to match up with student ID. They're separate from student ID. Those numbers on the very left are the row numbers. So when you call in the data, each line of the data will be assigned a row number. We don't really talk about, in the booklet or the videos, talk about row numbers that much. It's not just as simple as describing the number in the data set as it is right now. It can get a little bit more complicated than that, and whether you include them or not. So we're not really going to go into that or use them that much. I'm just pointing out that that's what they are there. It just happens to be that student ID, the cases are numbered 1 to 110, which is why they should match up with the row numbers. Yeah, so the output from head is the first 6 lines. In the opposite sense, there's also the function tail. So tail will do the last lines of the data set, so the last rows. And both head and tail have a argument called n, where n is the number of rows it prints as the output. The default value is 6, so that's why when I did head of pulse data, 6 values came to the screen. Whereas if I do tail of pulse data with n equals 4 as the second argument, I get the last 4 lines of the data set. So that's lines 107, 108, 109, and 110. So this can be just a quick way. You can use head on the data just to see what variables are there and what values they're taking. And you can just see tail to see what the end of the data set is. Again, you might find these functions useful, you might not. It's just good to know they're there in case you ever need them. So that's the top and the bottom. Now we can look at the variable types in our data set. So there's 2 ways to do this. Well, actually, there's many ways to do this, so I'll just talk about 2 of the common ways. Up in our environment tab, there's this little blue arrow. next to pulse data. If we click on that, it's like a drop-down menu, and it then describes all of the variables within pulse data. So all the rows below pulse data are the names of the different variables or the columns. So we've got student ID, height, weight, age, gender. And then it also describes what type of variable it is. So we've got student ID and weight as integers. Sorry, student ID and height as integers. We have weight as a number. We've got age as an integer. As we talked about in video 1, there's not that much difference between integers and numbers, besides the fact that we know integers will only be whole numbers. The different read functions will sometimes favor one type over another. So because student ID and height are all whole numbers, read CSV has made them integers. Whereas weight, if you look at her column here, was perhaps stored differently so that it has a couple of cases where there's a 0.5 in the weight there. So that's why it was called a number, so as not to lose information. It made a number, but all the variable types that were whole numbers were made integers. Again, not much difference between them. There's no information lost, and there's really not many ways it's going to affect us at all. We can see here that our categorical variables have been made factors, which is very useful. And then we've got some other variables down here, which are all integers. So we can see that here, and then we can also see the first few values in the column. So we can see that student ID starts at 1, 2, 3, 4, etc. Height, the first few values are 173, 179, etc. And the factors, it tells us how many levels of the factor there are. Then it starts to tell us what each level is, and then depending on how much room you have in your window, it'll start giving you the integer values that match those levels within the column. Because remember, we talked about in the first video that factors store a vector of integers, so 1s, 2s, and 3s, etc., of what the data is, and then it has another vector which says what a 1 means and what a 2 means, etc. So in this case, for gender, we can see we can just see on the edge there that the first two values are 1 and 1, and we can see the two levels are female and male. So this means that the first two values of gender are female and female. If we were to look at the actual data set, we'd see yes, the first two are female and female. It's just that R is storing it as 1s and 2s internally, but showing us the female and male label. If you want to see another way to see the types of variables we have in a data set, we can use the Str function, which stands for structure. So the Str function, the output of that is basically the same information we see in the, that environment tab, where you can see that pulse data is a data frame, contains 110 observations of 12 variables. Each of the variable names then below with the type of data that's in that variable and the beginning of that variable. So that's different ways you can see what's in your data set and what type of information is in there. Okay, so how do we access and refer to parts of our data? So we can use the $sign to refer to a specific variable vector. So the way data frames are constructed is that each variable is its own vector, but the data frame knows that a row in a data frame, so that the element of the same number in each of the vector relate to each other. So we can kind of see that down here in the str output, how each of the variables is next to a $sign. So a $sign allows us to access a variable from a data set. So if we see here, we have pulse data, which is the object, and we have a $sign, and we have age, which is the name of the age variable. So I want to highlight that, run, and the output of that is the vector that is the vector of ages. So they're the ages within age, the age variable, 18, 19, 18, 18, 18, 22, which matches the vector output here. One useful thing about especially RStudio when we're perhaps writing code for the first time is that if we have a data set in our environment, so we have pulse data, thankfully RStudio is very nice and gives us autocomplete options, so pulse data. If I go $, it'll then give me all the variables that are in pulse data, so I can go down with my up and down arrow and go through them, so I can find the right variable I'm after. And that's how I can choose how to access variables. Like I said just before, each variable is its own vector, which means the output of getting pulse $age, getting that vector, I can take that output vector and put it into a function that requires a vector input. So the function main, which we talked about in the first video, how it requires a vector input. If we were to have main bracket pulse data $age, that $sign is going to extract age from pulse data and output that vector. And that output is then going to go into the main function. So if I highlight that line of code and Control Enter, I can calculate the mean age to be 20.56, or 20 and a half, just over 20 and a half years. So that's how I can run a summary statistic or really get an understanding on variables within my data set. I can know I can access a variable in the data set and get the vector out with the $sign, and I can use that output into the main function or other functions like it. If I want to get more specific than that, I don't believe we looked at this in the other videos, but square brackets is how we access specific elements of vectors and also stuff like matrices and data frames. So the pulse data age, I'm just going to highlight that part, as we've already seen before, is the whole vector. But if I want just the fifth element, which in this case is going to be 18, 19, 18, 18, it is going to be an 18. I can have this square bracket right after age, so no space. There's no spaces on either side of the $sign, and there's no space between age and the square bracket. The square bracket and a 5, close square bracket, and this line, adding that 5 there in square brackets means I'm after the fifth element of age, which in this case is 18. If I wanted to change that, so again, this was using the up key, go up to the previous line of code, and I can change that, make it the sixth element. It means the output of that is 22, which is the next one across. So that's how I can get out of the variable specific elements. This might be because I want to know the value at a certain point in the vector, or I want to take out specific information from that vector and pass it on to another function. A lot of these little things here might not seem like they're doing much that's useful, but we're just displaying and demonstrating and building skills to use in R, and we'll use those skills when we get to the bit more interesting, meaty things. So again, this may seem not that important, not that useful, but we're just going over basic skills on how to access data and how to do different things that'll become much more useful later on. So the next line here is how we access multiple specific elements at once. So this 4:8 here, what that colon actually does is it means it's a shortcut to generate a sequence between the two numbers either side of it. So if I just highlight that 4:8 and go Control Enter, the output is a vector of numbers from 4 to 8 in a step of 1. Kind of like using the sequence function, so that's the SEQ function, from 4 to 8 by 1, but we can just use the colon. And by putting that in the square brackets, that vector of index numbers, that'll take out of age the ages at 4, 5, 6, 7, and 8. So if I highlight that whole line of code now, I can see that the 4th, 5th, 6th, 7th, and 8th age is 18, 18, 22, 20, and 18, which matches up to what I see up here earlier with the whole age function. Now, to put different numbers into those square brackets, I need them to be stored as a vector. So 5, when I typed 5 by itself within the square brackets, 5 exists essentially just as a vector of one number. Don't really need to do much. The colon, that makes a vector of numbers from 4 to 8. But if I want to combine numbers in different ways, maybe skip a few numbers, I still need to have a vector go into those square brackets. So in this next line of code, I'm going to use the C function to make a vector. And what I'm actually going to do is within that C function, which we learned about in the first video, the C function makes vectors of what I put into it as input. It's going to make a vector of the numbers from 4 to 8, and then also the numbers from 14 to 21. I can combine them that way. If I just highlighted the C function there and did Control Enter on that, I can see my output vector of numbers goes from 4 to 8 and then 14 to 21. So that vector going into the square brackets means I'll get out the ages that match up with those index numbers that's in my vector. So my cursor's on that line, Control Enter, and I can pull out the ages that match up to those numbers. Again, this may not seem that impressive, but it's just, I'm showing ways we can combine different skills to access what we want in R. There's other ways to access ages, or not access specific elements from a vector. So say I wanted the ages of the people in the study. So this is a pretend study of students that had their pulse measured before and after some exercise, or with some other information recorded. Basically say that I wanted the age of these students, but I only want the ages of the students who smoke. So what I can do is I've got my pulse data $age there, because I'm working with that vector of numbers. But then in the square brackets, I can use a logical statement to make a logical vector, and then only the values that are true will be pulled out of age. So here, I'll just do it step by step. So the smokes variable, so that's pulse data $smokes, is made up of a factor, it's a factor variable of no's and yeses. So you can see a lot of no's and a few yeses. And I want to use a logical statement to make an output logical vector that's true when smokes is yes, and false when smokes isn't yes, essentially. So if I highlight all that's in the square bracket there and Control Enter, this output vector of true or false values matches up. So false is where there was a no in smokes, and true is where there was a yes. Notice that I had to have yes as all lowercase, because that's how yes was stored. Also, just notice here on the left here in the console, I mentioned this in the first video, these numbers in the square brackets in the console, in the output from the code we run, they match up to the elements within the output vector. So it always starts with 1 because the first element is what we see. But this 29 here means that this no is the 29th element. And down below here, this 19 means that this true is the 19th element. This can be useful if we want to try and see how these two outputs match up, because obviously they're not being printed at the same proportion. There's not the same number of values per line when they're printed to the console because of the different sizes of yes and no and true and false. So if we want to make sure, for example, that this true here matches up with a yes up here, we might double check and count backwards and make sure that it matches up via the indices. Yeah, so using this vector, we can access just the ages that correspond to students who said yes to smoking. So putting it all together, highlighting the line code and hitting Control Enter, we get the ages of the students who smoke. Just one technical thing, The vector we put in the square brackets, if we're using a logical vector, has to be the same size as age. If the vectors are different sizes, they can't match up properly. We can't get all the, we won't, if they're different sizes, if we have too many trues and falses, we don't really know what we're doing. R doesn't know what to do with those. And if there are ages that don't match up with a true or false, R doesn't know what to do. So it needs them to be the same size. Because a data frame, which is what pulse data is here, has a requirement that all variables are the same size, we don't run into this problem. We know that smokes and age will be the same size vector, which is why we also know that smokes is equivalent to yes will be a vector of the same size, because each element of the output will match an element of the input, and we can work that way. So just keep that in mind with, remember to what you're putting into the square brackets, that it either has to be like a logical vector of the same size or a vector identifying specific indices to extract out of the vector of interest. Now, we can also use square brackets to identify columns and rows within the whole data set. So rather than just specifying through the $ and the variable name, we could just get specific elements out of pulse data using the square brackets. So this might be getting the first 3 rows and the first 4 columns, and only those that are in the first 3 rows and the first 4 columns. Mentioned in the first video, R identifies location first by row and then by location. Most languages do that. So here in the square brackets, I've been using 1, 3 to be 1, 2, and 3. And I'm using 1, 4 to be a vector of 1, 2, 3, and 4. So because I identify rows first, it'll get row 1, 2, and 3 out, and then I've got a comma, and then columns 1, 2, 3, and 4. So it won't be the whole column and it won't be the whole row. Because I'm using both of them, it'll just be the cross section where they're both true, where that overlaps both of those. So if I highlight that line of code and hit Control-Enter, I get the first 3 lines of the data set, and then that's just the first 4 columns. So that can be a way to get a specific subset of data out, identifying specifically by row number or by column number. We can identify which columns are which, potentially by going onto that variable over here, hovering over the variable and seeing what column number it is. So column 1 to column 4. If we wanted to identify or pull out of the data set just specific rows that wasn't in a sequence, we can use the C function here. So C 1, 5 will make a vector of just 1 and 5. But if we want all the columns, what we do is we still include the comma here, but we just don't put anything after the comma. So if we were trying to use square brackets to pull things out of pulse data, because pulse data is technically a 2-dimensional object of both rows and columns, to use square brackets, we need to have a comma in there to first identify the row condition and the column condition. But because in this next example, I want all the columns, I just won't put anything in there, but I still need that comma. So if I highlight that line of code, the output is the first and the 5th row and all the variables of the data set. I acknowledge that I might be going through this quickly. Normally in the workshops, we'd be taking this much more slowly, asking if people have questions, talking about things. So feel free to pause and rewind the video at any point and refer back to the booklet. I'm just gonna keep going because, you know, if I ask for questions, there's no one here to answer me. Cool. The next little example I have here is using logic just to extract rows. So here I have pulse data exercise equals high. So that's pulse data $ exercise is equivalent to the character value high in all lowercase. So that vector will be a character vector that has the same number of rows as pulse data, which means that a true or false value will match each row in the pulse data, and only the values that are true, those rows will be extracted. And then I can also pull out columns just by the variable name rather than the number. To do this, I still need a vector. So I'm using C here. And if I make character values that match the variable names, I can pull out just those variable names. This here, the C function, makes a vector that has the elements, a character value of student ID, a character value of pulse1, and a character value of pulse2. And that matches the variables in my data set exactly. Of course, R is case sensitive, so it matches exactly. If I highlight that line of code, I get the rows, just the rows that belong to students with high exercise, and I just get the variable names that I specified in my vector. So that's student ID, pulse1, and pulse2. Again, this might seem like little things that if all I'm really doing is just pulling out data, it's not that useful. I get that we're not really at the analysis stage here. I'm just showing you skills on how to access your data and how to play with your data and look at your data. These are all little skills that we're going to build on as we learn how to work with R. Okay, next thing we're going to look at is missing data. So if missing data is a very important thing with data sets to know what missing data means and how it can be stored. So if in our original data file, that CSV file, there's lots of different ways we could have had missing data. We could have had just a blank cell. That cell could have had something in it like a space, or it could have had a code to signify that the value is missing, like 999, some value that's very unrealistic. 999 and say a space are both values. So they'd come up as data here, and then we'd have to go through and change it to missing. What missing in a data frame is, it's got this value called NA. So that's how missingness is stored. This basically means that in this variable, in this row, there's no information that should match this row. The next bit of information in this variable will only match the next row. So we have something called an NA at that point for that variable and that row. If you're not familiar with NA, this might just sound like gobbledygook, apologies. But we'll hopefully get very familiar with it. So one function to see if I have NAs in a variable is the function is.na. So is.na takes values or a vector of values and outputs true or false. So here I got is.na and the pulse1 variable from pulse data. I can see that almost all the output in the vector is false except for one value of true, which basically means that at that element in pulse1, there was an NA value. So there was a missing value of pulse1 for that row. And if I count across, I can see 73 was false, 74 was false, 75 was false. So there should be index 76 in pulse1, so row 76. Go to my data, go down to row 76. And I can see, yes, pulse1 and pulse2 are both missing. So there's no information there for pulse1 and pulse2 for subject 76. So that's a way to identify where missing is. Of course, if I had a really long variable, and the output of is.na was also very long, I might not necessarily scroll through looking for the trues. One function I can use is the any function. So that's any, a, and y. And if I put into any a logical vector, like the logical vector that just came out as my output, any will return either true or false. So if any of the values given as the argument input is true, the output of any is true. But if all of the values that are given to any is false, the output is false. So because there is one true here, I'll highlight that line of code and run it. The output of true from any means that there is at least one true in the vector of logical values that I put in. The any function is basically just saying, well, from what I've given as the argument input, is there any trues? So that can be a way to really quickly check if there is any true values from a logical statement, which can be useful for things like data cleaning, not just for identifying missing values, but also for checking for logical conditions, checking for weird things in the data that doesn't make sense, and then seeing, is any of this condition true? If I didn't want to scroll through and find where that NA was, or like say it was a really big data set and scrolling would be unrealistic, or perhaps there were many instances of NAs, what I can do is using that same is.na function output, so the output of this function here is the same as before, is that logical vector. Putting that in the square brackets for student ID means it'll give me the value of student ID that matches with the true values from isNA. So that'll give me ID 76. Again, I've just shown you a few different ways to find that row 76 has missing in it. So you may be wondering, why am I showing you so many ways? Well, in some cases, one way might be much better than other ones. So I'm just showing you a couple of different ways to look for where missing data might be, or you could change that to be looking for other conditions, and then identify, is there anywhere where the condition is met, and where is that condition met? So here, we basically looked, is there any NA in this variable of pulse1? Is there any at all? And then where is that? Both through visual looking inspection and also getting it out by accessing the specific index in the vector. Cool. The next little thing is getting some other just information about your data. Again, these may not be things that you necessarily want to look for when you are, say, analyzing a data set. But there might be little functions that are useful as you're working on different things. So the first function we've got here is length. So the argument input to length is a vector. So we've got our vector here of student ID. With our data set, because all the variables are the same length, we could use any vector. This is just the example I'm using. So length will tell me how long that vector is, and by extension, how many rows we have in our data set. Another function that's very similar is dim, which stands for dimension. So dim takes a whole data set or even larger object and tells me the dimensions of that object. So it tells me that there's 110 rows and 12 columns or 12 variables. Again, they both tell you similar things. I'm just showing you some very common, very easy functions that you might use in different ways. It's up to you. We're just building on our basic skills in R in this video. One very function that's very useful is col names. So col names gives you a vector of the variable names or the column names of a data set. So the input here is pulse data, which is a data frame. And then they've got the function col names, all one word. And the output of that function is a character vector of each of the variable names. So what you might do from there is you might do col names to get the variable names out, because you might want to copy that into other code, copy it into something else. It's very difficult to highlight things. You can't actually do that in the global environment tab. So this might be the easiest way to copy the name of a variable name. Or you might use this vector for something else as well. But that's just a way to get information for you to use. Okay, next thing we're going to look at is subsetting. So subsetting is where we have a whole data set that we then want to just take a small part of. So over here, the first thing, there's lots of different ways we can do this, so to stay from the beginning. So one way we can do it is with the subset function. So we can see here, there's the subset function that has round brackets right after the function name. The first input for the argument X is pulse data. Then there's the subset argument, which is a logical condition on how to break up the data set. So for starters, I'm just going to highlight this part of the line of code. So I've got the subset function, pulse data, which is the data set, and then here I've got a logical condition, which is pulse data gender equivalent to male. Actually, I might start with that. So pulse data gender equivalent to male. That will give me a logical vector of true and false values, where true when the gender is male and false when the gender is not male. Notice male is all lowercase, which is how I've got it in the data set. So that's the two argument inputs I need. So the subset function that contains the data set and the logical condition, it will output a data frame that has just the male rows in there. But that does not override my data set, nor does it make a new data set. So using the subset function won't change my data set. Very few functions will actually automatically change your data set. All these functions make an output. And then if we want to use that output, so if we want to use the subset that has just male data, we either use it straight away in another function straight away, or we save that subset as another object. So here, I'm saving that output as pulse data subset. So I want to highlight that whole line of code. Subset, I'll collapse pulse data down, and I can see here that I've got pulse data subset, has the same 12 variables, but now only has 59 observations. So that output from the subset function has been assigned to an object called pulse data subset. If I wanted to, the output of subset could have been saved as the object pulse underscore data, and that would have overridden that original data set, so that would have changed my data, and then I would only had the pulse data object that was now just the male students in the false data set, in that, fictional data set. But there's no way to undo that. Once you override a data set, there's no way to get it back unless you go back to the beginning of your code, call it in from the file again, and do everything you've already done to it, if you've made any other changes at all. So one useful thing then could be to, if you want to just work on a subset for a brief amount of time, is do what we've just done there and make a subset object. So you can work on the subset and then go back to the other object, which is the full data set. This is how R is sometimes different to other other statistical software, in that it can make data objects and make lots of them. So rather than having just a single data set where you change filters and subsets to see how much of the data you're using at one time, R instead can make multiple objects that can be different subsets and have different filters applied to them. So that's one of the main differences between R and other softwares. Apologies if that wasn't as clear explanation as possible. Another way to make a subset is using the square brackets that we were using earlier. So like before, when we used a logical condition in the rows to identify specific rows, and how we then had a comma and no column numbers or names, the output of just using that square bracket of the logical condition and then nothing after the comma on pulse data is the exact same output of that data frame of only male rows. And if we want to save that, we can just save it as pulse data subset as well. So I'm saving the exact same thing as the exact same object, just using a different method. So both of those are very simple methods to make a subset of a data frame and then save it as another object. Whichever one you want to use is fine, they'll do the exact same thing. Some people prefer to use the subset function. Some people prefer the square brackets. There's really not that much difference between them. You can use whichever one you like. Myself, I tend to go more square brackets because I'm just used to dealing for whatever reason that way. It's really up to you, whichever one you like more. It may seem like R has a lot of redundancies this way, and there's different ways you can do things. But that's also one of the reasons R is great, is because you can have that flexibility to do what you like best as well. Okay, so the next little thing we'll do is just look at some quick summaries of our data. So one super useful function in R is this summary function. Now, there are many different types of summary function, and they'll generally depend on what input you give to summary. So you can put lots of different objects within summary, like you can put a data set like we're doing now. You can do a statistical test that you've saved, or a linear model that you've saved, which we'll address in later videos. I will figure out what type of summary you're generally after. But if we're looking just at the data set, and I highlight this, the summary function will, for each variable, give me a really quick summary of that variable. So see here for height, because summary has recognized that height is a numerical or integer variable, it's done a 5-number summary, so a minimum, a first quartile, a median, a third quartile, and a maximum, and then also a mean of that vector of numbers. So that's a really quick way to get a lot of information about that variable. And then over here for the categorical variables, it's giving me the counts of each level of that factor variable. So I've got 51 females and 59 males, 99 don't smoke, sorry, and 11 do. When you start getting lots of levels in a factor, summary may not show all of them, just as a heads up. And down here for pulse 1 and pulse 2, it's also told me how many NAs they were. NAs don't get included in the mean, the median, and those types of calculations. I should have probably mentioned that earlier when we were talking about NAs. NAs aren't included in analysis because it's recognized that's a missing value. It's not included. So stuff like functions like summary will automatically ignore them and just let you know that, hey, there was an NA here. Some other functions will give you errors, because while it doesn't include NA as a number, it says, hey, I don't want any NAs here. You need to deal with that first, either remove it or you can do something else with it. We'll talk about that in later videos. But yeah, so summary is a really quick, good function to just get an understanding of the data you have in your data set and the variance it has and distribution it has. It can be a good way to get an idea of any weird values. So if we had a height here of 5 centimeters, or an age of 6, when we're mostly looking at 18 to 40-year-olds, or if we had a pulse of, say, 15 or 300, it might look weird, and we could pick that up from looking at a really quick summary. Many other functions we can use to summarize data, but we're just looking at really quick ways to get a handle and an idea of the data we're looking at. Okay, the last thing we'll do is just do some basic plots. So one thing that's really useful to get an understanding of data is histograms. So a lot of these basic plots we're going to do here, I'm going to call the plots kind of uglyish. They're not the most attractive plots. Future videos will look at how to make really aesthetically pleasing plots. The plots we're going to do just now are just the really basic quick plots you can do in R. And we will also show how you can change them a bit. So if you want to make a really quick report but also has information in the plot, we'll do that. But future videos will show better ways to make plots as well. So just a little bit of both. So the first function here to make a histogram is hist. And the first argument x, which we don't really need to include x, we could do without it, but whichever way we want to do, is the vector of values we want to make a histogram of. So here we're going to do it for weight. So Control Enter on that line of code. And over here in my plot window, I've got a histogram of weights in the data set. So you can see here that most of the weights are around 50 to 60 kilograms. One very low one skews off to the top there. Now X, or that argument of the values, is the only thing that's super necessary. Everything else can be default done by R. So R has default done a title, which is histogram of pulse data $weight. It's got pulse data $weight down there as the axis label. And it's decided its own breaks and labels for the bins within the histogram. Stuff like that we can override with other arguments. So here in this line of code, we've got the same thing of X equals pulse data $weight. We've also decided where the breaks are. And then we can also decide what the main title is using the main argument, what the Y limit is, so as to where the Y scale goes to. We can also give our own labels. So just because we're making a really quick plot that we might chuck in an email to send to a colleague or put in a really quick report, but maybe not put into a paper, we might still want the label to be informative. So we're going to put weight in kilograms, and we're going to put labels equals true, which will put labels on the histogram. So if I highlight all that line of code, hit Control Enter, I now have a much better histogram with a title, with a label that's more explanatory, a Y-axis that's a bit more useful, and then I also have labels for each bin saying exactly how many cases are in each of them. If you'll notice here, my code went across 3 lines because I could have fit it all in one line of code. I would just have to scroll across. The way to do this for these big functions is that the line has to end in a comma. If the line ends in a comma and we haven't finished all the finishing of the round brackets yet, I will know to look to the next line of code. So ends in a comma, finishes there, and we'll keep looking through them. Okay, so the next little plot we'll look at is a box plot. So if we wanted to make a really quick box plot, we can just use the box plot function. So just box plot, all one word. And here we're going to make a box plot of height. So that just makes a really quick plot of the box plot of height. So box plot obviously being the main line in the middle of the median, the box being made by the first and third quartile, and then the min and maximum of solid lines, but also outliers identified outside of that as well. There's all sorts of calculations that go into identifying what's an outlier, which can be overridden the more you look into it. But again, we're not really looking at that right now. We're just looking at really quick ways to inspect the data. And like before, we can add other things such as titles, labels, and everything. We can also compare data between groups. So that's another thing we'll often do with box plots is we'll look at the distribution of the continuous variable like height across different groups. So see here in this next box plot, I have a formula input, which is equal to, and this is our first introduction into R's formula notation. So I'm not using vector here, so I'm not using pulse data $height. My formula is just height tilde gender. And because both of these names here match exactly the variable names in my pulse data, which I'm giving as my data argument, I will figure out how these two objects are related to each other. And then with all these other inputs, which we've talked about before. So if I highlight that line of code, I get a box plots where 2 box plots are made, one for female, one for male. And I've got some labels there, a main title, and R has figured out that it wants height compared between genders from my formula notation. We'll talk more about formula notation in future videos. The last thing we'll do really quickly is basic scatter plots. This is where we've got 2 continuous variables and we want to make a plot of how the 2 relate to each other. So there's 2 ways we can do this. So what we can do first is both of them using the plot function. Plot is another very versatile function, but in this case, it's going to make a scatter plot for us. So for plot, we can have two vectors as our two arguments. So our first vector will be our x information, or our x variable, and then the second vector will be the y variable, or the variable that's on the vertical axis. So if I highlight that line of code, Control Enter, I have a scatter plot here, pulse 1 across the horizontal axis and pulse 2 across the vertical axis. Alternatively to that, I can use R's formula notation, which again, we'll talk a bit more about in future videos in a bit more depth. But rather than x comma y, I can do y tilde x, and this will have the exact same output, just formatted in a different way. Talk more about this in future videos, but basically it's just a carry on from different people developing R, so different disciplines. Some people really like to split up vectors as different arguments. Some statisticians and mathematicians like the formula notation, which is very useful once we get to modeling. So it's basic plotting like this is kind of the overlap between everything. Again, of course, like before, we can always add lots of other things to the plot, like a main title, a subtitle, an X and Y label. And then if we were to look up the documentation for plot and look at all the other arguments we can add to it, there's all sorts of things we can change. I won't go through all the arguments I'm plotting here. This is just more of a demonstration to show that I can do all sorts of things by look up the documentation and look up all the possible arguments that I can change and change it to however I want. I'm not saying you ever necessarily want a plot like this, but hey, it's possible. So that's this video. Again, what we've done here is a lot of different things, a lot of like base skills that we'll build on other videos. So nothing there is like generally that impressive, really, but it's just building different skills which we'll put together in future videos and in future sections of the booklet if you're working ahead by yourself, on how to put different R skills together to do different things. Definitely encourage you to look at the past videos if things weren't clear here. Look ahead at the future videos, work through the book, and remember to do the examples and activities in the book, because the best way to learn R is by doing R. I can't stress that enough. Thank you very much, and see you in future videos.